Hello and welcome to my video. Okay, so I just wanted to do a quick little video to do with basically injecting signals into old radios pretty much, because it's actually a kind of an annoying thing which you can really screw up horrifically on, and it wouldn't matter so much if you didn't destroy, well, whatever instrument you was using to generate that signal, right? So in old radios, one of the very, very common things for aligning it, and pretty much all of them that I know of, is of course injecting a signal directly into the IF, right? The IF tube, bypassing the tuning and such. This is so you can line it to get the maximum amplitude, or signal out, I guess, if you like. Doing this requires putting your signal generator, whatever you're using to generate the signal that you're injecting into a radio, directly onto the control grid usually, or sometimes a plate, it depends, right? Basically, what they want you to do is just use a capacitor. It's almost always 100 nanofarads, or 0.1 microfarads. Right. And this will go to your signal generator, and this will go to whatever thing you're testing. This allows the AC to go through, which is going to be higher frequency, usually 455 kilohertz, which is that will just pass right through the capacitor, and the DC will get blocked. Now, there's many ways of doing this. It's almost like going onto like how we protect voltmeters and multimeters and such. The most common one is you just do a diode clamp. See up here, where you have two silicon diodes, or whatever diodes you're using, going to ground, right? In this configuration. This way it gets both the positive and negative part of the waveform. So you can just pretend it is around 0.6 volts. Of course, this depends on the current and the heat that I run, but it doesn't matter. It'll protect it either way. I don't know any signal generator which should die at 0.6 volts DC. But nonetheless, okay, and that's a simple way of doing it. The problem is there'd be no current limiting if you've done this without any resistor beforehand or after. Doing this without current limiting means if this capacitor completely breaks down on a radio's B+, you're going to get the full output of that radio through them diodes. Hi. Okay, so this video here is just to show the demonstration of the circuit board I've done a little bit ago. I'm going to allow you to see the scope. It's the exact same design. I think I just said it's a 1 kilo resistor with the capacitor and the two diodes. Okay, here's a good screenshot, hopefully. Somewhat of a screenshot, I guess. On the horizontal scale is 1 millisecond per division, and the vertical is 2 volts. Okay, so here we go. Okay, as you can see, it's limited to about 800 millivolts, and that is the maximum amplitude present at this point. You can see the little transient here. Oh no, it's a bit higher than that. The voltage peak to peak was lying. It's actually about 1.3 according to that, which would be this spike here. And yeah, that's to be expected. Again, they don't conduct exactly at 0.6 volts. It's a little bit ahead of that, depending on the current flowing through them at the time. It is limited pretty greatly, however, by that resistor and capacitor, the capacitor being the highest impedance part of the circuit. And this is what the signal generator would be seeing if everything went wrong. So you can see the very fun little spikes that happen. This is probably due to the switch more than anything, really, I imagine. Because the switch I'm using is, of course, just a mechanical switch, not an electrical one. That's how it's going to be with contacting stuff with probes and such. And you can clearly see the effects. It's pretty interesting. If we zoom in around this peak, let's see what it looks like, shall we? Okay, this is the peak zoomed into. It's a bit annoying. I don't know why it doesn't ever allow me to do that. There you go. Now, one's off the way. Anyway, so as you can see, there's the peak. It's very spiky, and it's got a lot of transients in between it as well. Loads of little spikes, as you can see. Look at that. Pretty nasty, eh? The scale right now is 20 microseconds per division, so you can see, just for reference, how fast that is.